pedagogically you are introduced to differential calculus before integral calculus in any course on mathematics, you might be excited to know that integral calculus was studied far before differential calculus was formally introduced. In particular, the ancient Greeks started studying this notion of integral calculus back in 600 BC to 300 BC, when they were interested in determining the area of a region which is not a rectangular region. So what kind of area they were looking at is as follows. So suppose that you are given a function fx, so on an interval, so suppose you have a closed and bounded interval ab, and f is a function from ab to r, and suppose you have plotted the graph of this equation y equal to f of x, and you want to determine the area which is bounded above by the graph of the function y equal to fx, bounded on the left hand side by this line x equal to a, on the right hand side by x equal to b, and below by x axis. But then how do we compute the area of this region? Even before computing the area, how do we even define the area of such kind of a region? So this kind of things were studied by ancient Greeks, as I said, in between 600 BC and 300 BC, whereas differential calculus was not properly formally introduced before 1680 AD. So what we are going to do in our next couple of video lectures is that we are going to introduce to you how integral calculus is actually studied without using differential calculus. So you already know from your childhood that if you have a rectangle, then there is an obvious notion of area of the rectangle. If the rectangle has length L and height h, then you know that the area of this rectangle is given by L times h. So we are going to assume three very intuitive axioms in order to tackle the problem of determination of area of regions that are interesting to us, that I have just described. So what are the three axioms? The three axioms are very intuitive. The first one being the area of a rectangle, as I just mentioned, that if a rectangle has length L and height h, then the area of the rectangle is given by the quantity L times h. Now bigger the region, bigger the area. So what do I mean? This is our second axiom. So if R is a region which is properly contained inside another region S, then area of R is less than or equal to area of S. And the third part says that if I can break a region into several parts, so which I have written in terms of union, but it is not exactly the union. So if R can be broken into n parts, R1, R2, Rn, provided that this regions intersect only at boundary points, then the area of the full region, so area of this whole region, is equal to the sum of the smaller regions. So you may grant me these axioms just like that, because these are so intuitive, and we will see that how we will be able to make sense of area of regions of this type by just using these ideas. And all these things are just at the heart of integral calculus. So let us proceed. So here we are going to use a method which is called method of exhaustion, which was actually studied by the ancient Greeks, as I have just mentioned. So what is exhaustion? So if you want to look up in the dictionary the meaning of exhaustion, one of the meanings is that a state of extreme physical or mental tiredness, but this is not exactly what we are looking at. What we are going to do is that we are going to use our rectangles as building blocks, and we are going to exhaust the area that we started our journey with. The region, we are going to exhaust the region by several rectangles. Note that by our first axiom we know that area of so how can we determine the area of these rectangles? By the third axiom, we can actually compute the area, the sum of the area of all the rectangles, and in turn we can determine the area of the network of this rectangles. So network is like a colloquial word for the union of all these rectangles, and of course we will always make sure that the rectangles that we are going to take are always intersecting each other only at boundary points. So in principle, what we are going to do, we are going to going to construct two networks of rectangles. So two networks of rectangles. So one of the networks of rectangles will be just contained inside the region that we are interested in, and another network of rectangles will be containing a region that we are interested in. And from this picture, what you can make out easily is that the area of the white rectangular region is little bit smaller than the area of the region that we are interested in. Of course, if we can make sense of the area of the region, but we will somehow keep our intuitions alive. And of course, by similar reason, using the second axiom, we can say that the area of the green rectangular region, which just contains our region, is just bigger than the area of the region that we are interested in. Let me now give you a concrete example which give or take something that Archimedes studied back in the period of 300 BC roughly. So what he was trying to do is that he was trying to compute the area of regions which are bounded above by a parabolic curve. So what is a so y equal to x square is a parabola, and we are interested in the region which is bounded above by the parabola, on the right hand side by the line x equal to 1, on the left hand side by y axis, and below by x axis. So we are going to employ our method of exhaustion. So let us take it up slowly, because this is more or less a motivational lecture. So here is the region that we are interested in, and we are going to cover this, or we are going to create two rectangular networks which will help us in computing the area. So what do we do at the very beginning? So first we draw a very simple rectangular network consisting of just one rectangle. So let me first draw the green rectangular network. So what I do is that I leave the picture as it is. I choose the highest point that the curve has in this region, draw a line which is parallel to x-axis, and from this point I draw a line which is parallel to y-axis. So this way I get a rectangle. And what is the area of this green rectangle? So I call this number u1. So, and you can see that this point is just 1 1. So this rectangle has uh, length of the base 1, height of the rectangle is also 1, so u1 is exactly equal to 1. And since our region that we are interested in is contained inside this green rectangle, we can say by our second axiom that area of our region that we are interested in is less than or equal to u1. Next, what we do is we pick up the smallest point in the region. So the smallest point on the graph of this equation y equal to x square in the region, which here unfortunately happens to be the origin, and we draw a line which is parallel to x-axis. So again, since the point is already on the x-axis, the line parallel to x-axis will be going to be x-axis itself. So here we have somehow constructed a rectangle with height 0, and consequently the area of this white rectangle that we have just made up is going to be equal to 0. Now let me call this number L1. So I think I have convinced you that the area of this region that we are interested in is bounded between 0 and 1. Now let us do a bit more. Let us be a bit more careful and do a little better argument. So here, so what I do is that I divide the base of the region into two equal parts. So okay, so this is going to be 0. Okay, so this point is equal to half. So first I have to construct the green rectangle. So how do I construct the network of green rectangles? So when I choose this point half, I draw a line which is parallel to y-axis. Now this line divides our region into two parts. What I do now next is that I pick up the first part of this region. I choose the highest point on the graph which lies in our first region. So here it is this point. Draw a line which is parallel to x-axis towards left hand side. Similarly, what we do is that we take the highest point on the second region, draw a line which is parallel to x-axis. So this gives us a network of two rectangles, and we see that our area of R is less than or equal to the area of this green rectangular. So area of the green okay, so let me not write green. So area of let me call this rectangle R1, R2. So area of R1 union R2. We know that R1 and R2, these two rectangles, intersect only at boundary points. So this is going to be equal to area of R1 plus area of R2. So can we compute area of R1 and R2? Well, we can. So we know that each of the rectangle has length half. So so what I do to compute area of R1 is that I have to take half times the height of R1 and also half, because this is the length of the base, half times height of R2. So what is the height of R1 to begin with? So for that we have to find the y coordinate of this point. And what is going to be the y coordinate of this point? Well, we already know that the x coordinate of this point is half, and since this point is on the parabola y equal to x square, this is going to be 1/4. So 1/4. What about the height of the bigger rectangle? Well, this is somewhat trivial. This point is 1, 1. So half times 1. So this is the height of the big rectangle R2. So this is just 1/8 plus half and 5/8. So you can see that the area of R, just our intuitive notion of area of R is less than or equal to 5/8. Now we do the same thing with our network of smaller rectangular region, and let's see how do we compute it. Again, we have this partition of the region. So for the first partition, we take the point on the graph which is the lowest point on the graph. So here unfortunately it is this one, so this does not contribute anything here. So I call this rectangle S1. So this is kind of a hollow rectangle, so there is nothing and this is just a line. And what do we do for the second part? So again we take the smallest point here and draw a line parallel to x-axis towards my right. Okay, fair enough. So now we have a rectangular network. So we can see from our second axiom that area of S1 union S2 is just less than or equal to area of R. And how do we compute this area? So this is area of S1 plus area of S2. What is area of S1? 0. Area of S2, we know that the base of the rectangle is equal to half. And what is the height of this rectangle? This will come from this y coordinate of this point, and this is nothing but 1 by 4. So what we get is 1 by 8. So I have probably convinced you by now that area of R is less than or equal to 5 by 8 and is better than or equal to or greater than equal to 1 by 8. Note that here I have used two partitions, and this gave me a somewhat better approximation of area of R than what we previously had, where we only used one partition, so to speak. So you can see that this estimation is far better than our initial estimation. In fact, what I am not willing to show you by calculation, but I have just written it down. If I use use a partition where I have divided the base of the region into 1000 equal parts, then you can not you but a computer will show you that area of R is bounded below by this number 0.3328335, and area of R is bounded above by 0.3338335. Now why do I mention it separately? There is a reason. So we know that if I want to approximate this area up to 2 decimal places, you can already see that here the first 2 decimal places is 0.33, and here the first 2 decimal places is 0.33. So AR is approximately equal to 0.33, correct up to 2 decimal places. So this method, as you can see, that it gives me good approximations of the area of the region that we are interested in. Okay, so now instead of dividing the base of the region into 2 equal parts or 3 equal parts and going ahead with the small calculations, let us think like how a mathematician will think. Let me say that I am going to divide the base of the region into n equal parts now. So n is an integer. So I will calculate these numbers ln and un, and we will from our intuition or from our axioms, we will claim that AR lies between un and ln. So let me now just calculate an expression calculate an expression for un and also an expression for ln. So un comes from this bigger rectangles, network of the bigger rectangles. So let's see what we have done. We have divided this thing, this interval 0 1, which is the base of the region that we are interested in n equal parts. So what are the points on the x-axis on the partition? These are 1 by n, 2 by n, 3 by n, etc., n minus 1 by n by n. So how do we compute these things now, un and ln? So the computations are not very difficult. Let me first assure you this. So we know what are the length of the base of each of these rectangles. And what is that? That is always going to be 1 by n, because we have divided the interval 0 1 of length n into n equal parts. So to compute the area of this bigger rectangular region, all we need to know is that we need to know the height of all the rectangles. So let us try to do this one by one. So what I have to do now, we look at the first big rectangle. So the x coordinate of this point is 1 by n. The point lies on the graph of the function y equal to x square, so this is going to be 1 by n square, and consequently the height of this rectangle, the first rectangle, is going to be 1 by n square. So what is the area of the first rectangle? This is going to be 1 by n times 1 by n square. What is going to be the height of the second rectangle? You can now easily check what we are going to do. So 2 square by n square. So 1 by n times 2 square by n square. So we go on like this. We go up to 1 by n times n square by n square to have parity, but you can easily see that the height of the last rectangle is exactly equal to 1. I have just written down n square by n square to make sure that it is in the same form as in the other rectangles. Okay, so I can take out 1 by n cubed, and then we are left with 1 square plus 2 square plus blah 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 n square. So this is the area of the network of bigger rectangles which cover our region. And how do we compute the area of this region? So here we have to compute the area of this rectangle, this rectangle, this rectangle, etc., so which are given in white. And again, the first one here does not contribute anything, but we will write it. So let me write 0. So, and then what is the area of the next rectangle? We have seen that this is determined by the y coordinate of this point. So 1 by n square. So 1 by n plus 1 by n times 1 by n square, plus then this is determined by this point, which is given by 1 by n times 2 square by n square, etc., 1 by n times, and here we are going to use this point, and the coordinate of this point is n minus 1 by n minus 1 by n whole square. So n minus 1 whole square by n square. So writing this expression in a rather nice form, what we see is that this is 1 by n cubed times the first term is 0, does not contribute anything, so 1 square plus 2 square plus, and this sum goes up to n minus 1 whole square by n square. Okay, so what we have done using our axioms is that we have bounded our region, or the area of our region R, between these two quantities un and ln, and we have computed the areas of un, or we have computed the expressions un and ln. So let me now go forward, and the point that I want to make here before going forward is that this is true for all n. You take any natural number, 1, 2, etc., this is going to be true. Now some of you might also be understanding where I am going with this, but first let me see what I can do with these numbers. So we have so let me compute what is un minus ln. So this is the expression that we had got from un, this is the expression that we have got from ln. So if I do a simple subtraction, we can see that all these terms get cancelled with the first n minus terms here, and all we are left with is n squared by n cubed, which is 1 by n. So what in principle this gives me is that limit as n tending to infinity un minus ln is 1 by n, which is equal to, so equal to limit n tends to infinity 1 by n, which is equal to 0. And that gives me the fact that limit n tending to infinity un is equal to limit n tending to infinity ln. Now this is a totally algebraic formulation of un minus ln. Let me just give you a geometric perspective of this. So what is the area in this picture, or what is the number? How do we get this expression un minus ln? You can see that un is the area of the bigger rectangles, the network of the bigger rectangles, and un is the area of the network of the smaller rectangles. So this will be useful, this geometric intuitions. So what is un minus ln? So let me use a different color here. So for this rectangle, un minus ln is this region, area of this region. For this rectangle, it is this region. For this rectangle, it is this region. For this rectangle, this region, this region. So what we can see is that you can, if you just, so we know that the length of the base of each of the rectangle is the same. So if you want, you could just copy and paste this small rectangle which contributes to un minus ln here. Similarly, what you can do, you can just copy and paste this rectangle over here inside this rectangle. So this was like this. So you can again copy and paste this rectangle over here. So you can see that all the rectangles fit very nicely on the big rectangle, or the rectangle which is given in the right hand side. So the sum of area of all these let's say error rectangles is exactly equal to the area of the biggest rectangle that we have in our picture. So, and what is the area of this biggest rectangle? Well, we know that the base has length 1 by n and the height of the rectangle is 1, and consequently the area of this rectangle is 1 by n. So this is exactly what we are getting here, 1 by n, which is the area of the biggest rectangle. Well, we have now seen that AR lies between ln and un, and this is true for all n bigger than or equal to 1. So if we want to take limit as n tends to infinity, so from your calculus 1, you will see that since AR is a constant and we are going to take these limits, we will see that this is also true, that limit of un n tending to infinity is bigger than or equal to AR, and this is limit n tending to infinity ln. But we have seen that limit of un as n tends to infinity is same as the limit of ln as n tends to infinity. So these two sequences go to the same limit. And what is this limit? This limit, and our sandwich theorem says that AR must be equal to this limit, the common limit that we have. And so the moral of the discussion is that AR can be just computed by taking limit of either un or ln. So let me try to compute the limit for you. So what do we have here? This is limit n tending to infinity un. We do have an expression here for un. So un was 1 by n cubed times 1 square plus 2 square plus blah 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 n square, and we know an expression for this thing. So 1 square plus 2 square plus blah 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 n square is given by n times n plus 1 times 2n plus 1 divided by 6. So this is limit n tending to infinity 1 by n cubed n times n plus 1 times 2n plus 1 divided by 6. If you want to compute this limit, I am sure that you have seen this limit in your calculus 1. So what I will do is that I will take 1 n from here in each case, and we will divide into this thing. So this is n by n times n plus 1 by n times 2n plus 1 by n, and this 1 by 6 is constant, so this can come out, and we'll see that this limit is 1, this limit, so let me try to do it completely in this example. So this is going to be 1 plus 1 by n times 2 plus 1 by n, and this limit, this goes to 1, this goes to 2, and consequently the product goes to 1 over 3. So this is the area the of the region that we were interested in. So what we have just shown is the fact that the area of the region that we started with is exactly given by 1/3. So a fun exercise that you may try now on your own is to compute or is to perform the same thing for the function if x is equal to x cube.